Hello learners, welcome back to the course on deformation processing of materials. So in the previous class, we had seen the relations for forces in extrusion process. And after that, we solved some numerical examples. And after that, we started the forming process known as deep drawing. In that, we saw what is meant by deep drawing. We saw the schematic of the setup for deep drawing, and then we saw parameters like the drawability and limiting drawing ratio, etc. Okay. So now let us extend our discussion to some more parameters related to the deep drawing process. So today we will see anisotropy, which will involve normal and planar anisotropy. Okay. So let us begin the discussion today. So we will now see anisotropy in deep drawing. So the anisotropy parameter, normal anisotropy basically, it defines the resistance to thinning in the sheet metal. So it was discussed in the previous class that there is a limit to the drawability, and also we had seen that the thinning of material may lead to failure. Okay, so that thinning is basically measured or is restricted through planar anisotropy. Okay, so it is represented by R. Let us see what is normal anisotropy. It is represented by capital R. This capital R is different from the one which we saw earlier, that was in case of extrusion, and that was extrusion ratio. This capital R is related to deep drawing, and it represents the normal anisotropy. Okay. And it is the resistance to thinning in thickness direction, or the direction normal to plane of sheet. Resistance to thinning in the direction normal to the plane of sheet. Normal to the plane of sheet. Or the thickness direction. Or thickness direction. This is basically a ratio of strains in the width to the strains in the thickness direction. So mathematically it will be capital R will be the ratio of strain in width direction. So we will consider true strain here. So it will be W naught by W. Actually, if we consider the true strain in terms of length, then final length divided by initial length would be there. But here a sort of change is taking in a way that it represents the change in width. So to correct it for the negative values, we will take in reciprocal. And since here we are taking W naught by W, in the denominator also we will take the initial value by final value. This will be change in thickness, and thickness we were representing by h. So this is h naught by h. So this term defines the normal anisotropy in case of deep drawing process. Here W naught is the initial width, and W is the final width. Similarly, H naught is the initial height, initial thickness, and H is the final thickness. So these are the parameters. Also, if we substitute the change in thickness, because it is difficult, most of the times it is difficult to measure the change in thickness. So what we can do, we can implement the concept of volume constancy, and by that we can replace the change in thickness with change in width and length. Okay, so in that way we can rewrite this equation, and let us see what happens in that particular case. Okay, so by using constancy of volume, these changes can be written as, this will be W naught, L naught, H naught. This will be equal to W, L, H. And from here we can say that this H naught by H will be WL by W naught, L naught. Okay. So we can substitute this back in the above equation, and therefore this R will become ln of W naught by W over ln of WL over W naught, L naught. And if we take the negative sign in the denominator, it will get reversed. But let us keep it in this way only. So this can be written as ln of W naught by W over, if we want to separate, then we can separate out, or we can simply write it as it is. This is W by W naught into L by L naught. So this is the new relation for normal anisotropy. Also, there is a term known as planar anisotropy, which is the averaged value for these normal anisotropy values taken along the 0-degree direction, 45-degree, not direction, at 0-degree angle, at 45-degree angle, and at 90-degree angle. Okay, so the planar anisotropy is given as planar anisotropy, and this is given as R bar is nothing but this is the weighted average basically. So R naught plus 2 times R45 plus R90 by 4. Sorry. By so this relation gives us the planar anisotropy. Okay. Earlier one was normal. To understand it better, suppose we take a rule sheet and we cut samples from it at in 0 degree, 45 degree and 90 degree direction. And cut samples in 0 degree, 45 degree and 90 degree. So say this was the sheet. So a sample like this will be along 0 degree and one like this will be along 45 degree and say this is along 90 degree. This will happen when this is the ruling direction. Ruling direction. So in this case, R0, R45 and R90 will be the normal anisotropies in 0 degree, 45 degree and 90 degree samples respectively. Because R0, R45 and R90 are normal anisotropies values in, let me write values for 0 degree, 45 degree and 90 degree samples. Okay. So this gives us the planar anisotropy values. So we have seen the anisotropy and we have also seen the limiting drawing ratio. So to correlate these two, there is a diagram which is basically a sort of straight line. So let us see that diagram also. So how is it drawn is say on the y-axis we have the limiting drawing ratio. So on the x-axis there will be the planar anisotropy. So if this is the limiting drawing ratio, here we will have the planar anisotropy. This will be like this. And the graph basically will be a sort of straight line. Say on the x-axis we have values like 0.2, 0.4, 0.6, 1, 2, 4, 6, etc. Okay. So if we draw a straight line at 1, just for easy visualization, then this type of the curve basically will be of the nature like, let me put some values on the y-axis also so that it will be easier. Say this is 2 followed by 3 followed by 4. So these will be some sort of straight lines. So the main curve will look something like something like this. So this will be basically a type of straight line. And several elements will lie along these lines. Okay. So how the elements will be there? See, here lies zinc, here lies the titanium, and near to this region will lie the aluminum, copper, here steels. Let me increase the axis a bit. To say this is 3, this is 4, this is 6. Okay, so this is something like this. This diagram represents the relation between the limiting drawing ratio and the planar anisotropy. So values of this R bar or planar anisotropy for steel range from around 2.5 to 3, and for aluminum it is around 1 to 1.5. Let me write it here also. For steels, R bar is in the range of 2.5 to 3. For aluminum, R bar is around 1 to 1.5. Okay. And this gives us one more important information, which is basically a sort of extra tip for you. So you would have observed that both the zinc and titanium elements are HCP. But have you ever thought why is it difficult to deform zinc as compared to titanium? Means upon deformation, zinc undergoes fracture or failure, while it is possible to deform titanium to some extent. So what could be the reason behind this? Okay. So the reason for this is the C by A ratio of zinc and titanium. Okay, so this is, let me put it like a note. So this was a question that titanium is easy to deform, okay, but zinc is not. Titanium is easy to deform, but not zinc. And both are accepting. Why is it so? Why is it so? So the reason for this is the C by A ratio. The C by A ratio of zinc is higher. So while deforming, it undergoes fracture or failure. So while deforming, it will fail or break. It will break. But for titanium, C by A is relatively lower, so this can be drawn. C by A is nearly 0.6. Okay, so it can be drawn and on. So this was the reason behind non-formability of zinc and formability or possible formation for titanium. So now let us see some of the defects which are observed during the deep drawing process. Okay, so what happens in deep drawing is that many times the stresses are not uniformly distributed, and sometimes problems like thinning may occur, which may ultimately lead to failure or fracture of the surface of material. Okay, so the major defect, if we say, is formation of a crack in the blank. Okay, so that will basically lead to structural disintegrity and will ultimately lead to disposal or wastage of the blank or the component being formed or deep drawn. Okay, so now we will see the defects in deep drawing. So very first one is the development of a crack. Development Ment of a crack, which will lead to structural disintegrity. Okay, which ultimately leads to structural disintegrity. And this usefulness of the material may also get hampered by the process of necking or buckling or wrinkling, etc. Okay, so another defect is thinning or necking, buckling, or wrinkling. So these are also the defects which are observed in deep drawing operation. Again, there may be defects arising due to the elastic recovery or spring back of the blank, and that will lead to dimensional instability or uh, lack of dimensional tolerances may lead to this type of failures. Okay. So another one is failures due to dimensional tolerances. Okay, so basically it should be insufficient dimensional tolerances, sufficient dimensional tolerances and spring back. Okay, now one other important failure which is observed or defect which is observed in the process of deep drawing is the separation of lower portion of the cup or the bottom of the cup from the remaining portion of the cup. And the main reason behind this is the high stresses at the sharp radius of punch. Okay, so sharp punch radius may lead to the separation of bottom of the cup, separation of the cup bottom from the rest part. Okay, so this is one of the major defects observed. Now, one more important defect which is observed in case of this deep drawing process is the earring defect. Okay. So basically, earring defect, how it appears, let me draw it schematically for better visualization. So suppose cup like this has been formed and there is a concentration of stresses over here. So this portion may try to wrinkle out. Okay. and ultimately earrings will be formed on the exposed or above part of the cup. Okay, so they will appear something like this, and ultimately this part now needs to be discarded only. Nothing can be done for this, so this needs to be cut and separated or discarded. So these are earring defects. And reason behind this defect is again the planar anisotropy behavior. Here the relation is something different. Let me write down that expression also. So here this is delta r, and this is r naught minus 2 times r at 45 plus r at 90 divided by 2. This relation is a little bit different from the one that we saw for planar anisotropy. This is also for planar anisotropy, but the relation is based on the loading conditions and stresses acting over there. Okay, so what happens here is when this delta r is 0, there is no earring, and or no earring defect is observed. No earring. But for higher values of r, this delta r, as it keeps on increasing, earring becomes observable or dominant. Earring occurs. Okay. And if, as I mentioned, if earring is formed, then the portion where earring is there needs to be cut and removed. Nothing can be done. So if earring is formed, then the portion where earring is formed is portion has to be cut and removed. So this was regarding the planar anisotropy and some of the defects which are observed during the deep drawing operation. Now, related to this deep drawing process, there is an important test which is done for sheet metals in laboratories, so as to observe their behavior. How are they performing when subjected to forming process like deep drawing, etc. So the test is known as Ericsson cupping test. So let us briefly see how that test is done and what is the setup for that. Okay. So we'll now see the Ericsson cupping test. Ericsson cupping test. So let us see the setup for this and how the cracks are categorized. So suppose there are two dies. It is similar to the deep drawing setup. The fundamental arrangement is same. Okay, so these are two dies, and on these dies we will put the blank, which will be later formed using the punch. So say This is our blank. And it is supported by blank holders. It is kept in place using blank holders. Like this was done in the deep drawing operation. And a punch is used to form a cup out of it. Okay, so there will be a punch. Let me mark the punch with some other color. So say this is the punch. And it presses it down. So this is the punch pushing it down. And ultimately this blank will convert into a cup or will form a cup. So now there will be a formation of a cup here. Say this is the final shape we are getting. Okay, so this is the final shape, and this was my initial blank. So here a force F is applied here, and this, let me label these. So this is the punch. This is blank holder. This is the blank. Okay, and these are the dies. And this entire thing is supported on some platform, say like this. So this is the schematic arrangement for Harrison cupping test. And this punch will be something like this. There will be a ball attached here, a hard ball, which draws the blank. So it will be like this, some 10 mm dia ball. So this is the punching. And all this thing, this arrangement, preparation of samples, etc., are done as per the ASTM standards. ASTM code 643 and 64309. ASTM E 64309. This particular standard is used for this Harrison cupping test. Samples are made. As per this standard only. So The drawing here is carried till fracture, till crack is initiated and the material fractures. So there is a possibility of formation of two different type of cracks here. Okay, so either a circumferential crack may form, which will be circular in nature, and along the circumference it will be formed, and the other crack type may be a flat crack, which may form anywhere on the drawn surface. Okay, so if we try to draw them, it will be something like, say this was my blank. So not the entire blank will be drawn. Its portion, say central part, a size similar to that of the ball will be drawn, or to punch will be drawn. Okay, so say this was my blank. So its central portion may get drawn and some crack may get formed over here only. Okay. Say this is like this. So circumferential crack may form, and how the blank will appear from, if we take a section, then this type of appearance will be there after the Harrison cupping test. Okay. So this D basically is measured here, and it is known as the Harrison index number. Okay. And the cracks may be of two types, as I mentioned earlier. This is D. It is the Harrison index number. Index number. So the cracks may be of two types. The cracks may be of two types. First one may be the circumferential cracks. The cracks around the circular circumference. Okay. This will be isotropic cracks. Isotropic means similar in the entire circumferential direction, or in the entire circumference. So this will be short of isotropic. And they will have circular type of fracture. Circular fracture. Okay. And the other type will be flat cracks. Okay. This may be on any section or any part of the drawn region. On the drawn part. Okay. And these are anisotropic. Also, D is known as Ericsson index number D. So this was something related to the Ericsson cupping test. Now let us see the relation between the diameter or radius of blank and the diameter or radius or dimensions of the final form product in some common shapes which are formed out of this operation. Okay, so relation between diameter or radius of blank and drawn product. Okay, so we will consider some very common shapes which are formed out of this drawing operation. So let us first consider the case of simple cup. Okay, so what will happen here is the blank will be transformed or will be drawn into a cup type of shape. Okay, so say this was our blank, so its diameter will be dB. Let me draw it again properly. Okay, so say this is the blank, and it has diameter as dB, blank diameter. Okay. So what will be the area of this blank? It will be pi dB square. Area will be pi dB square by 4. So pi by 4 dB square. Now when it is converted into the cup, that will appear like something like this. So let us assume it to be cylindrical shape, perfectly cylindrical shape. Though there may be some radius of curvature here at the bottom, but now let us consider it to be perfectly cylindrical type of shape. So say this is the cup. So here the diameter of cup will be DC say. So this will be the diameter of cup and its height is say h. This is h. So now how the area will be related? Initially, entire blank had the area which was pi by 4 dB square. But after the formation of cup, this area is now equal to the area of the curved region plus the area of bottom surface. Okay, so if we equate the areas, we will have this pi by 4 dB square, which will be nothing but the summation of area of bottom of the blank, which will be not bottom of blank, it will be bottom of the cup, which will be pi by 4 DC square because the new diameter is DC, plus the curved area, and curved area we know that for cylinder is pi dh or 2 pi rh. So here pi dc into h. Okay, so pi gets cancelled from all of them, and if we write this blank diameter in terms of the blank radius, then it becomes 4 rb square, and the 4 gets cancelled by 4. Here also, if we replace the diameter by radius, again it will get cancelled out. So this will become radius of blank is nothing but the square root of radius of cup square plus 2 times radius of cup into pi. I have replaced the diameters with respective radii. Okay. So this is the relation between the radius of blank and the radius of cup and height of cup. Okay. Now let us see the second case for a bowl shaped or hemispherical type shape. So let us see for bowl now. So again, initially the blank will be of similar kind, say with the initial diameter db. Okay. Again, area will be pi by 4 db square, and after forming, it will be converted into shape of bowl. It will be hemispherical. We will consider it to be hemispherical form. So basically, this type of shape is formed. Okay. And here again, now the radius becomes, say, capital R. Okay. So now, how the area will be related? Here, area will be the area of this hemisphere, which is nothing but 2 pi r square, because the entire surface area of a sphere is taken as 4 pi r square, and since it does not have any flat surface over the hemisphere, only the hemispherical shell is there, so area will be 2 pi capital R square. So if we equate the areas, we will get, let me change the ink color. So this will be pi by 4 dv square will be nothing but 2 pi capital R square. Again, if I replace this dv with the radius of the blank, it will become, firstly pi we cancel out, then it will become radius of blank square is 2 times radius of this hemisphere square, or simply we can write it as radius of blank will be root 2 times the radius of hemisphere. So this is the relation in case of a bowl type of shape. Now again, let us see some seed for one more case, that is, suppose a conical frustum is formed. Frustum is a type of section of a cone. Means in case of cone, it has a vertex and the slanted regions extend. But in case of frustum, it is cut from the vertex side. Means vertex will not be present. It will be a section or part of a cone. Yes, you can search on the internet for frustum and you will get very nice diagrams, so you can visualize it. So in case of a frustum of a cone, C is conical frustum. Conical frustum. So in this case, again the initial blank was similar, say like this. I'm drawing it elliptical, but it will be a circular blank with diameter dB. And now this gets converted into a conical frustum like this. Okay. So here there will be two diameters. Say this bigger diameter is D2 and this one is D1. So this one is D1 and height here is H. Height is H here. Now in this case, what will happen? If we equate the area, this will be again pi dB square by 4. Pi dB square by 4. And now we will have to take the area of this curved section as well as the bottom area, because it has been deep drawn. We have not removed the bottom portion. It is again a sort of normal water glass of steel, if you have seen. That is the frustum of, or that is a conical frustum. Okay, so in this case, the bottom area is pi by 4 d1 square, and the curved area here will be pi times the average of diameters multiplied by h. So pi will get cancelled out from everywhere, and this will become dB is nothing but under root of d1 square plus 2 times d1 plus d2 into h. This is by simple rearrangement of the above equation. Okay. This 4 will cancel out and 4, 2, 2. Okay, this is fine. So this gives us the relation between the blank radius or blank diameter and the dimensions of the drawn products. Okay. Again, there is a term known as the strain or strain in case of this deep drawing. This is a little bit different thing from normal strain. So let us see it also. So basically, if it is calculated in a similar manner like initial diameter minus final diameter over initial diameter, this will give us the strain. So if we take initial dia minus final dia, this diameter is of the blank, okay, divided by initial dia. This will be the strain. Okay. Or mathematically means using symbols, we can represent it as dB minus, say d1 is the final diameter, and again divided by dB. This will be the strain beta. This can help us to determine the number of passes or number of strokes required to get the desired thickness or reduction or dimension. Okay. It can be further rearranged like 1 minus d1 over dB is beta. And we know that dB over d1 will be the drawability, as we have seen earlier. Okay. So this d1 by dB is known as reduction ratio here. This reduction ratio will be d1 by dB. This is another term. As I mentioned, it can help us to determine the number of strokes required. So let us understand this thing by an example. Okay. So say we have beta or strain as 0.5. Okay. So if beta is 0.5, then how many strokes are required to form a cup of 70 diameter out of a blank of say 200 diameter? So the beta is this, and suppose we have a blank of diameter dv is say 200 okay, and we are converting it to a cup of say diameter 70 okay. So how many strokes are required? How many strokes are required? So let us see how it happens or how can it be solved. See, if we try to reduce it forcefully in a single stroke, then the material will fail. It will not take the proper shape before getting the proper dimensions. It will fail. So we need to go stroke by stroke. Okay, so say we in the first stroke we go to diameter d1. Let us say after first stroke dia is d1, then if we apply the above relation of this strain, what we get is 1 minus d1 by db will be 0.5, because we have to keep the strain as 0.5. Okay. We can go to this much straining only in one stroke. So if we substitute the values, what we get, this d1 by db is 0.5. Okay, so d1 will be 0.5 of dB or half of dB. So d1 is nothing but half of dB. So d1 is dB was 200, so d1 will be 100 So in one stroke we can reduce up to or we can go up to 100 dia. Okay, so we need to go for one more stroke. Now let the dia be d2 after second stroke. Okay. Then what will happen? Again, if we apply the above rule, 1 minus d2 by d1, sorry, we will have to consider db only. So db, this will be 0.5 again. And now when we substitute the values, this d2 over db will be, this will not be db because here we are starting from d1. Okay, so here we will have to consider d1 only. Okay, so again this will be 0.5, and if we substitute the values, this d2 will be half of d1. So d2 is 50 because d1 came out to be 100 So here now we can see that now we can go up to 50 dia in the second stroke. and we had to go to 70 mm. So in the first stroke, we cannot achieve 70. We will have to go for 2 strokes so that we can reach 70 mm. Okay. So this strain gives us an idea of number of strokes. Okay, so we can write it also that thus in the second pass or second stroke, the dia reduces to 50 mm. 50 mm, but not below 100 mm in first stroke. 100 mm in the first stroke. So we need 2 passes or strokes for this. Okay. Therefore, 2 strokes or passes are required. Okay. So this made it very clear that how this strain is very much effective in determining the number of strokes. Okay, so we will stop now and we'll begin our or continue our discussion in the next class. Thank you, everyone.